is a joint program, for those that know me. I'm James, and I was quite excited by the sort of theme of this follow-up program where we're sort of talking about open problems in either side and sharing some of our favourite problems. So back just before the pandemic at the joint math meetings in 2020, I had lunch with Larry Guth, and I didn't really know what to talk to him about at lunch, so I sort of pitched to him a problem that was very close to my heart, coming from number theory, but could be phrased purely in terms of harmonic analysis, and we chatted about it quite a bit, and then email follow-ups, and that led to something that I was very happy with, where we were able to make progress on a question connected to large values of Dirichlet polynomials. So I'm just going to basically use my talk to try the same thing again. I now have multiple harmonic analysis in the audience, so I want to pitch some of my favourite problems coming from analytic number theory that can be phrased in terms of questions to do with large values of Dirichlet polynomials that can at least partially be thought as pure harmonic analysis problems. And I would be super interested in any progress on any of these problems, or also any reasons why we might expect progress to be particularly difficult. So if any of you have any ideas, I'd be very, very happy to talk to you. Okay, so the general problem that I'm interested in is, it's called the large values of Dirichlet polynomials problems. So we are given some real parameters, a large number n, a large number t, a number sigma strictly between 1/2 and 1, and maybe I will say a one-bounded sequence of, let's say, complex numbers going between capital N and 2 times capital N. So given these parameters, we're going to let W be a subset of T under T2, such that when I form the Dirichlet polynomial an n to the it, so if you're a harmonic analysis, maybe you'd prefer to think of this as the sum from n to 2n of an e to the it log n. So these finite sums of some coefficient times n to the it are often called a Dirichlet polynomial, and I want to assume that this is taking a large value. So the left-hand side here, I'm thinking of as a function of little t, and I'm going to say it's large. So large is determined in terms of this parameter sigma as to how large it is. Sigma equals 1 would be there being essentially no cancellation of this being the largest possible value, but sigma being a bit smaller than 1 means it's moderately large. And I'm assuming it's large for all points t in the set W. So I have this Dirichlet polynomial, which is large, where large is defined in terms of sigma, so it's sigma large for every point t in the set W, and I want to, the question then is, what is the best upper bound for the size of W in terms of n, b, sigma. So hopefully the question is clear. I'm just asking for large values of sorts of objects. Implicitly, we're expecting that as you're looking for larger and larger values, these should occur less and less frequently. And most of the time, we won't be too concerned about any terribly specific one-bounded sequence, and we'll think about it as an arbitrary one-bounded sequence. So this isn't really about too much about the properties of sequence. So just to give some context for this, there's a conjecture. So I'll call this conjecture 1, which is due to Montgomery, which is essentially the conjectured correct answer for this general question. That the Montgomery conjectures that W should be bounded above by t to the little 1 times n to the power 2 minus 2 sigma. In practice, I'm not normally interested in big uniformity issues, so I'm thinking of n as being t to some fixed power. It's the sort of scale that I'm normally most interested in. But Montgomery's conjecture is the sort of conjectural best answer to this, and it's not too difficult to show that there's various different examples that meet this bound. So you can construct sequences, one-bounded sequences, AN, for any choice of sigma and any choice of capital N, and any choice of capital T, for which you have a lower bound of the same order of magnitude. So this would be the best possible answer, but since you're looking at large values or level sets of a function, a natural way to try and approach it is to look at moment estimates. And Montgomery also conjectures what the moment estimate should be. So there's essentially no real difference between looking at discrete sums over one-bounded points and continuous averages. So I'll write this as continuous average. So under the same assumptions, if I look at this Dirichlet polynomial raised to the power kappa, and I average it over all possible values of t, then Montgomery conjectures that this should be bounded by t to the little o1 times t n to the power kappa over 2 plus n to the power kappa. And again, this would be a sharp bound if it was true. If I chose my ANs to just be plus or minus 1 at random, then you can show that virtually all the time this Dirichlet polynomial has square root cancellation, so this should be of size n to the half for all values of t, and so we'll give a contribution of this size. If I instead organise my ANs so that there was one single point t where there was no cancellation whatsoever here, say choosing AN to be n to the power minus I t0, some fixed value of t0, then in a small neighbourhood of t0, I'll get a contribution of size n to the kappa, which would then be matching this term here. And so conjecture 1 complies conjecture 2. Which in turn implies a slightly weaker upper bound of the form t to the power 2 minus 2 sigma plus little o1, just by choosing kappa to balance these terms. So both of these conjectures are hard in general, and so I'm not really expecting anyone to make complete progress in solving these conjectures. If you're a harmonic analyst, then Both of these are hard. So if you're a Harmonic analyst, maybe evidence for this claim is that Bourgain showed that conjecture 2, so the weaker one, implies the Kikeya conjecture for tubes in arbitrary dimensions. Morally, this is because if I look at a short partial sum over an interval and choose, maybe at first sight, the coefficients to all be a constant on that interval, then these entity ITs look like a geometric series, and so these sums over short intervals then look like geometric series, and so they're large on some sort of dual arithmetic progression, which essentially looks like a tube. And so if I can pack lots of these tubes together into a small space, I can find lots of large values, and conversely, if I get good moment upper bounds, I can rule out the possibility that there will be lots of these tubes. So conjecture 2, I think, is certainly harder than Kikeya, but it's kind of morally very similar to Kikeya if you imagine the only way a Dirichlet polynomial can have large values was if there's some subsum that looks like geometric series. But anyway, obviously we're going to hear later on in the week about great progress towards the Kikeya conjecture, but nevertheless, if you think that Kikeya is hard, you're certainly going to believe that conjecture 2 is hard. For those people who are number theorists who maybe aren't so interested in Kikeya conjecture, it's also well known that conjecture 2, so again the weaker conjecture, implies the density hypothesis. For the unit zeta function, so this is the claim that the number of zeros row of the zeta function such that the imaginary part of rho is at least sigma, and the real part of rho is at least sigma, and the imaginary part of rho is at most t. This is bounded by t to the power of 2 minus 2 sigma plus 1. Essentially this thing bound here, and for the purposes of many applications to primes, this is almost as good as the Riemann hypothesis itself. So if you could prove this unconditionally, this feels a lot weaker than the Riemann hypothesis, but lots of the consequences for primes would be almost as good as the Riemann hypothesis. But this is another conjecture that seems difficult and out of reach. And moreover, if you're caring about specific incarnations of sequences, then you can rephrase things like the Lindelof hypothesis or the Riemann hypothesis in terms of these sorts of things. So the Lindelof hypothesis essentially corresponds to the claim that the sum of NTIT between n and 2n is bounded above by t to the 1 into 1/2. So this would be saying for the specific sequence where n is always equal to 1, you actually get an upper bound of 0 for whenever sigma is bigger than 1/2. But it never takes large values. And similarly, the Riemann hypothesis is very close to the claim that if I look at something that is essentially coefficients being primes, to avoid a few small technical issues, maybe I'll have, instead of primes, the one Maynard function, and I'll take off their average value 1. Then this is a sort of similar claim. So at least very difficult conjectures to do with the Riemann zeta function the Riemann hypothesis implies the Engelhoff hypothesis, which implies the density hypothesis, are all closely connected to this general question. Okay. So, hopefully I've convinced you that this is a general question that has genuine content to it. It would have lots of nice consequences if we really knew how to solve something like this. But this is a very difficult question in general. However, what I want to sort of emphasize today is that there's many specific incarnations of this problem for specific parameter values, which are very interesting in and of themselves, and for lots of these situations, making any progress beyond what's a so-called trivial bound would already have very nice arithmetic consequences, and there's no reason that I'm aware of to suspect that these sorts of questions are as hard as the Riemann hypothesis or the density hypothesis or anything like that. Yeah?
Do people know more about conjecture 2 if A and C equals to 1?
Yes, let me get back to you on that because I'm going to mention that in just a few minutes, okay? Maybe the short answer is that when n is equal to 1, you can essentially use Poisson summation to replace capital N with t divided by capital N. And this means that you can essentially concentrate on n just being less than t to the 1/2. And then if you're thinking of n being less than t to the 1/2, but not being very small, essentially we know nothing beyond just what we know for a one-bounded sequence. There's some technical results that are morally like a little bit more information for n equals 1, but for direct upper bounds for that moment, essentially not much more is known beyond this one trick of being able to apply Poisson summation to replace a Dirichlet polynomial of length n with a Dirichlet polynomial of length t over n, which is typically a good thing to do if n is bigger than t to the 1/2 and not so good otherwise. So that means essentially when n is equal to 1, we're able to understand the fourth moment. And so
well, I guess it depends on the size of kappa, right? I mean, if kappa is less than 4...
yeah, so we're able to understand the fourth moment and smaller, but we're stuck at going beyond the fourth moment.
But also you can do van der Korput, correct? If n is 1. You can kind of take moments, van der Korput.
Okay, but I don't think that's going to help with...
No, I'm just...
yeah, there's other things. I mean, there's a whole set of techniques you can use in general for Dirichlet polynomials, and yeah, when n equals 1, you can use, there's additional techniques that come to bear. But at least for the point of view of conjecture 2, yeah, essentially with n equals 1, our knowledge for general n is as good as our knowledge for n less than t to the 1/2, which in that context means that we can prove this when kappa is less than or equal to 4. Okay, but I mentioned a trivial bound, so let me just take a step backwards and say what the trivial bound is for these sorts of questions. So there's a trivial bound where we can just look at the second moment. And to set things up nicely in Fourier space, we can put in some majorants to majorize the integral between t and 2t, which maybe has a rapidly decaying Fourier transform, and then we can just expand out the sum, swap the order of summation and integration. You'll have coefficients that look like an bar, and then some integral w of t over capital T n over m power it dt, and this integral here is essentially rapidly oscillating, and so very close to zero if the fraction n over m is more than a constant over capital T away from 1. Constant here could be taken as 100 or something. But otherwise, we may be expecting there to be not a huge amount of cancellation at all, and so we can bound it by something which is just bigger of t, because this is an integral of length t. And that would then mean that we're counting pairs integers n and m, which is 1 plus big O, which differ by a ratio 1 plus big O 1 over t, with weight t, and this is t times n plus n squared, which is precisely Montgomery's conjecture in the case cap equals 2. There's one other small trick, that if I raise a Dirichlet polynomial to the kth power, this is also essentially a Dirichlet polynomial. Just because the n to the ITs are multiplicative in n. So there's a minor technicality that the coefficients can sort of slightly become larger than one bounded, but they can all be absorbed into these t to the negative 1 error terms that I have everywhere. And so it is also a Dirichlet polynomial. And this means essentially we get Montgomery's second conjecture whenever kappa is an even integer. So this is of length n to the k instead of n, and this implies Montgomery 2 for kappa an even integer. And this gives an upbound in terms of w of the form, so just in this case, it would be of the form n to the 2 minus 2 sigma plus t n to the 1 minus 2 sigma for the size of w. And again, replacing it by power, you'd have n to the k and 1 minus 2 sigma plus n to the k times 2 minus 2 sigma. So this is essentially what I call the trivial bound. And there's lots of different techniques that do better than the trivial bound in various different ranges. Some of them getting more and more sophisticated. One important one is the Montgomery hash technique, which to harmonic analysis is essentially the PG star method, which essentially improves on this bound when sigma is bigger than 3/4. It essentially improves this 1 minus 2 sigma to a 4 minus 6 sigma. But either way, these are short of the general question. But the key point of my talk for many sort of arithmetic applications, it is just specific parameters and beating the trivial bounds is relevant. And one might hope that beating this trivial bound should be rather easier than really answering the general question, particularly if we're interested in really quite specific values of capital N, capital T, I guess capital N relative to capital T, and specific values of sigma. And also maybe specific sequences AN. And so, in the second half of my talk, I'd like to just give a few different examples of incarnations of this general question, which are related to what I think of as important and interesting questions in analytic number theory. So let's see how I do with the chords. It's been a long time since I've used the German setup, so all that looks good.
It's the angle that's fine.
I need this after.
That's to the right. And the washing.
I think it's memories of Jörg doing a double. And it's okay. So challenge one is maybe a fairly simple one. It's the density estimates so this is progress towards the density hypothesis that I just raised here, which is very relevant to lots of questions about primes, but maybe particularly they're related to primes in short intervals. So this was the specific question that I pitched to Larry when we had lunch together at the joint meetings, and what led to that collaboration improves zero density estimates in the region when sigma equals 3/4. That was what was the limiting case then, with various applications of primes in short intervals. But as a consequence of our work, there's a new limiting case, and we tried moderately, but not very hard, to squeeze as much out of what our ideas would give. And so the key situation now is you're interested in sigma being 7/10, n being t to the 5/13, and in case it's relevant, your sequence an just in the sequence 1. And in this case, the trivial bound, which I just raised, would come from looking at the fourth moment here, and the trivial bound gives t times n to the power 2 minus 4 times 7 over 10. And the question is, can you beat this by winning a factor of t to the 1 over 1,000? So, in particular, my work with Goof does beat it if sigma is bigger than a certain over 10, but essentially is worse than the trivial bounds when sigma is less than or equal to a certain over 10. Our work doesn't use the knowledge of the coefficients at all. So we make no use of the fact that coefficients are equal to 1 in this situation. And we also don't really use, at all the fact that the value of n we're interested in is actually quite small. All we do is square the Dirichlet polynomial to get something of length 10 over 13, and then work with this as a arbitrary Dirichlet polynomial. And so we lose all this factorization structure in the Dirichlet polynomial, which in lots of other contexts is really, really important and useful. So, in other ways, you should be able to better when n is 5 over 13 than when n is 10 over 13. So you get exactly the same trivial bound by looking at the second moment when n is 10 over 13, t to the 10 over 13, as you get for the fourth moment when n is 5 over 13. So we essentially do something that works for 10 over 13 and then just immediately say that implies something for 5 over 13. So I guess for all of these, I may be morally writing out a key situation. Technically, I have no proof that if you prove something with these specific parameter values, then this has any applications. You need something that's ever so slightly more general than what I'm writing down. But morally, I feel that if you improve this situation, you're almost certain to make progress on the overall problem. I guess maybe the other thing that I'll mention is that if there was, we could improve this unless the additive energy of the set W is of a very particular size. Does do this. Unless the number of t1 plus t2 minus t3 minus t4 is bigger than 1, where the ti's are all in W, has a very particular cyclic side. I think in the critical situation, if it looks completely wrong, maybe I'm not 100% certain of that, but if I just chose 4 points in a set W at random, you know that the sum is going to be something between 2 and 2t, so if it looked completely random, you might expect there to be W to the 4 over t solutions. And I think we can do better unless that's clearly the case. So it's the completely random case situation that looks the worst from one point of view. I think. Okay, so that's challenge one. Hopefully the question is reasonably clear. You don't have to make progress on the whole general problem that I put up that I think is very difficult, just with these specific values, and I know of no particular reason why this problem should be super hard, beyond I've had a little think about it and I've not seen how to do anything. I'd also be super interested in any reason that anyone comes up with as to why this really should be a very difficult question, which is maybe going to be related to the third talk. Okay, challenge 2. And this is going to be related to moments of the zeta function. So we know that the integral between t and 2t of the fourth moment of the zeta function is bounded above by t to the 1 plus 1. We believe that all moments should be bounded above by t to the 1 plus 1. But maybe the next most relevant result is we have a bound on the 12th moment that's not of the conjectured correct order of magnitude. We have a t to the 2 plus little o1. Well, this is quite a difficult result, and just essentially from looking at a very small neighborhood of 1 point.
It's a bit hard to see that it's a 12.
Yes, I agree.
But it would still be true with 2.
It would still be true with 2, but maybe it's a slightly less deep result in that case. So just looking at a small neighborhood of a single point t would be given an upper bound of zeta of a half plus it of t to the 1/6, which isn't quite the best known, but is not far off from the best known, just as now infinity. But in particular, this implies that I'm looking at the kappa moment. This is bounded above by t to the power 1/2 plus kappa is 8 plus little o1 for kappa between 12 and 4. And this is the best bound we know for any of these intermediate exponents. And doing better than this is very closely related to large values of Dirichlet polynomials. And at least morally, the critical case, and I'm sure we'll hear a bit more about particularly this question in the next talk, in Max's talk. So the critical case, maybe unsurprisingly from this, is, at least in my mind, when you're looking at values of the zeta function that are of size essentially t to the 1/8, and we can show that this happens on a set of size t to the 1/2, and in particular, we're interested in the case when n is t to the 1/2. So in response to Hong's question, I mentioned that when the coefficients are all 1, there's a trick with Poisson summation that allows you to replace a Dirichlet polynomial of length n with one of length t over n, which often means that t to the 1/2 is a critical situation for lots of questions to do with the zeta function. We're looking at sigma equals 3/4, which corresponds to the zeta function taking values of size t to the 1/8. And you want to beat the trivial bound of t to the 1/2 fourth moment of the Dirichlet polynomial. And so again, a critical case for this, at least in my mind, the most important thing is really just when we hit the trivial bound of large values of Dirichlet polynomials. And again, here, in case you can make use of it, we're interested in the sequence AN just being equal to 1. Maybe I'll mention that the Maynard argument was sort of designed to work well precisely when sigma equals 3/4. Gives nothing in this case. Essentially, you have to be careful if you're looking at the square of a Dirichlet polynomial of length t, because unless you're making some use of the coefficients, then something like this fourth moment bound is meeting Montgomery's conjecture, including conjecture 1. And so we're getting sharp bounds if you're not using the coefficients and you're just squaring this Dirichlet polynomial, which is implicitly what we're doing. So because we're not using the fact that you're coming from a shorter polynomial and you're not using anything about the coefficients, that's why essentially our argument P denotes to give nothing in that case. Second attempt. Maybe I'm doing fine for time, so maybe I'll include the thing that I was certain about going to include. So maybe the final two challenge ones are going to have the same flavour of being up against a trivial bound, but have a slightly different flavour. So progress towards the Lindelof hypothesis. In particular, it's a result of Morgan, the theta of a half plus t is bounded above by t to the 13/84, which is a number which is a little bit less than 1/6. And this is using an elaboration of a fairly lengthy argument of fundamentally Bombay Fanny actually, there's lots of various refinements due to Huxley and others. But so maybe the critical case that I'm going to write down is normally a little bit further from a critical case in some sense, but to prove a bound of this, you typically want to show that when you have a Dirichlet polynomial of length n, you'll get a bound of into the half plus. So I'll get this is roughly equivalent. And often, morally, again, the hardest case is when n is equal to 2 to the 1/2. So actually, I think in sort of the precursor to organic work, it was maybe work of Huxley and Watt, and it wasn't t to the 1/2, it was a different case, but I at least would be very interested to see strong progress in the case when n equals t to the 1/2, and so this is corresponding to, if I did my arithmetic correctly, sigma being 17 over 21, which is about 0.8. We're trying to show that w is 0 in this case. So w when this value of sigma. There's various ideas, particularly related to things in spectral theory of orthonormal forms, that sometimes get sub-wild type sub-complexity estimates, and so progress towards linear would be a natural challenge. It's just trying to get an infinity upper bound for these sorts of topics. So I'm trying to show an infinity bound for these things. I'm trying to show for every value of little t between capital T and 2 times capital T, this sum is bounded by this in the critical range. And so that's corresponding to saying there's no large values that are bigger than this infinity bound. So this is going to be a very artificial way of shoehorning it into my original general question. Yeah.
Sigma does appear in the line equivalent to Brownian's bound, right?
Yeah, so I've written it in terms of n to the half and t, and then I'm translating this as I'm just trying to solve for sigma so that n to the sigma equals n to the half t to the 13 over 34 when n is equal to 2 to the 1/2. And if I did the arithmetic correctly, which I might not have done, that should be 17 over 21. Does the question make sense so far? Okay, and then maybe the final challenge I'll mention is progress on the zero-free region. Maybe this is rather more speculative than the other challenge problems, which I feel are maybe more approachable, using some new idea of harmonic analysis or somewhere else. But for the zero-free region, there's a method of Vinogrado which implies that the sums that we're looking at of n to the it, n equals n, 2 times capital N, are bounded above by n to the power 1 minus sigma 0, with sigma 0 roughly equal to log n squared over log t squared. And this is what's behind the best zero-free region. And in particular, this is non-trivial for, line slightly, but whenever n is a bit bigger than log t, when n is bigger than e to the power log t to the 2/3.
Kohlhoff as well.
Yeah.
It's really Kohlhoff, I think. Exercise seniority.
I'm not going to get into it. Yeah, so this is essentially what's behind the best zero-free region for the even z function, which also has lots of important applications to prime numbers. And again, it's an infinity bound, but now essentially the question is how small can I take n to get a non-trivial bound here, which is almost the opposite of these questions to do with the zeta function, where often we're interested in the essentially largest value of n and trying to get the best bounds possible. Here, we are interested in the smallest values of n and trying to get a non-trivial bound. Essentially, nothing non-trivial is really known for n less than equal to x log t 2/3, and so the challenge is just to prove some non-trivial upper bound when n is this sort of size. Okay, I think I'm almost out of time, so so maybe I'll stop here and see if anyone has any questions. So thanks a lot for this.